Here's our lab unit 2 manual. We go all the way to the end of this manual. We have this case study on human respiratory physiology. So this was something I asked you to try to complete before we had this discussion. And that's because there's going to be at least 3, maybe 4 questions directly related to this case study on human respiratory physiology, because it's related to the effects of carbon monoxide on the oxyhemoglobin dissociation curve. I don't know how many of you actually tried to answer these, but you will have to have these answered because it is technically part of your lab manual. If you look at what's listed here for your lab manual being complete, this has to be completed in order for me to check through your lab manual, and it's only worth 2 points rather than 4 points, but it's still on the list for a rubric there, which means technically it's part of your lab manual being completed, but it's actually lecture material in terms of what you'll be using it to study for, right? Okay, so our job right now then is to pick up and do this review of the carbon monoxide poisoning multiple choice questions from this clinical correlation that is in the back of the lab manual. And before we do that, however, I want to show you this curve. Let me blow this up. Maybe that will make it look a little less sloppy here. And let me get a different color here. This curve here, we looked at what an oxyhemoglobin dissociation curve would look like for somebody who had carbon monoxide poisoning. And in particular, I wanted you to pay attention to the 2 axes here, y-axes. So along the bottom, we have the partial pressure of oxygen, and we are ranging here from 0, 50 to 100 here in the center, even though it's not shown, to 300. So we're using the scale similar to what was in the homework packet from one of those diagrams. And then on the left side, we have the percent oxyhemoglobin saturation, 0 at the bottom, 100% saturation with oxygen here at the top. Right. On the right side, on that y-axis, we have the oxygen content, which would be milliliters of O2 per 100 milliliters of blood, or you can say milliliters oxygen percent. And at the very top, I have 20.1, which we would expect as an oxygen carrying capacity for an individual that had a normal hemoglobin concentration of 15 grams percent. Right. Then the actual diagram that's drawn here, the curve itself, the oxyhemoglobin curve, shows us that we have half the oxygen content of what we would expect for an individual that has a normal hemoglobin concentration. But it's totally possible that this individual has a normal hemoglobin concentration. What's the problem here, however, is that the individual with carbon monoxide poisoning has a reduced oxygen carrying capacity. Why do they have a reduced oxygen carrying capacity? Because carbon monoxide displaces oxygen from the hemoglobin molecule, right? It attaches at the same binding site, and so it's in competition for that binding site. And we know that hemoglobin has a much higher affinity for binding CO than it does oxygen. It will gladly bind CO over oxygen. And so if we just have a little bit of CO present, that CO will most likely bind to that hemoglobin and displace the oxygen. And so now that hemoglobin can't carry the same amount of oxygen. We have a reduced oxygen carrying capacity. So the oxygen content of the blood is going to be decreased compared to normal. And then the percent oxyhemoglobin saturation is going to be decreased, right? So we have less oxygen being carried. We have more CO being carried. And that's going to be shown here in terms of the percentage of the hemoglobin that is that's capable of carrying oxygen. So if we're at 50% saturation of hemoglobin with CO, so let's say COHB is at 50%. That means we're at 50% oxyhemoglobin, right? 50-50. And that's the example that I'm showing here, 50% saturation with carbon monoxide, 50% saturation with oxygen, right? So these are things that we would expect to see: reduced oxygen carrying capacity, reduced hemoglobin saturation with oxygen, and we'd also expect to see, compared to normal, a left shift in this curve, meaning that, that the hemoglobin itself has an increased affinity for the oxygen it's already bound. It doesn't want to let it go to the tissues. Right? And that's due to the much higher affinity it has for CO. It doesn't want to let the CO go. And if it doesn't want to let the CO go, the oxygen can't unbind either as readily, right, during unloading. Right. So I just wanted to point out some aspects of this here, because we're going to see a diagram very similar in that CO poisoning clinical correlation in the lab manual, right? Now, before we go on to look at that, let me just point out to you then the difference that we would see between that type of diagram and the one above, just so we're aware of some of the changes that we would expect with CO poisoning, but not in under other circumstances. For instance, this other hemoglobin, oxyhemoglobin dissociation curve, is one for an individual who has anemia. So based on the fact that they have anemia, we know they have a reduced oxygen carrying capacity. So we're going to show that their oxygen carrying capacity is lower than what we would normally expect. So that could be that they have less hemoglobin, right? A lower hemoglobin concentration, for instance. Maybe they have half the normal hemoglobin concentration, and if they do so, and that hemoglobin is fully saturated, then we're going to get half the oxygen carrying capacity, reduced oxygen content. However, assuming that they don't have a problem perfusion ventilation matching wise, right? So no cardiovascular disorder that would lead to that problem, no respiratory disorder that would lead to that problem, then they should be fully saturating whatever hemoglobin they do have, functional hemoglobin they do have, in the lung capillaries during transit, right, in gas exchange. So we would expect that hemoglobin to become saturated, right? And so what we would do then is we would change the oxyhemoglobin saturation axis. We would have to make it proportionally smaller here to show that even though their oxygen content is overall reduced, they're still fully saturating their hemoglobin at the lung capillaries. They're still reaching 100% saturation with oxygen, right? In this case, that's not a problem for them. That is a problem for an individual where there's CO present that's displacing the oxygen, right? And so in that case, we don't change that axis, the individual with CO poisoning. So those are just some basic differences I want you to be able to note regarding the oxyhemoglobin dissociation curves if I give you different scenarios, different patients, for example, on the exam. And then you would understand why you have a proportionally smaller axis here for oxyhemoglobin saturation for an individual with anemia, but not for one that has carbon monoxide poisoning, right? Maybe you've already done this already, or maybe you've been busy studying and haven't had a chance to do this, but I have posted Dr. Street's review. She did a review of these questions here, and it's the same basic review that we're going to do together now. You also have a key posted. This is my key. I'm showing you my key right now. That is posted on the external internal respiration page for Unit 4. And it's posted there because it's going to be covered on this lecture exam with this lecture material regarding respiration, right? Rather than the lab exam. You didn't see this information on lab exam 2, even though this is actually in the lab manual. So here is the page in the lab manual, starting on page 63. And I'm just going to blow that up a little bit. And so let's run through the problem here with Charles. If you have your answers, I'm going to just poll you to tell me what your choices are here for the questions, and we'll go over those together. So let's start with the case study itself. Charles returns to his apartment at 5 p.m. in the evening. He turns on his old kerosene-fueled space heater that never sounds good. And it's been a cold day in late spring. His third floor apartment was chilly, and that's why he's turning on this space heater. After spending an hour fixing dinner, he ate his dinner while watching the evening news on TV. He noticed that his vision became progressively blurred. When he got up to go to the kitchen, he felt lightheaded and unsteady. He became disoriented and then passed out. The next thing he remembered was waking up in intensive care unit in the hospital. Some friends had stopped by at 7 p.m. and found Charles unconscious on the kitchen floor. And luckily, it seems like Charles does not lock his door. Otherwise, I don't know how his friends got into his apartment to find him. But it's a good thing that they just let themselves in, right? Because otherwise, Charles would have been in big trouble there, having lost consciousness while breathing in carbon monoxide. So his friends ended up calling the ambulance. They rushed Charles in, still unconscious, to the hospital. Once in the hospital, they did an arterial blood draw sample. Oof, I'm gonna just draw right through that, right? Okay, so that's key. We're looking at arterial blood, and we want to compare these values here to what we know would be normal values for an individual, right? So we want to ask, for example, compared to normal blood gas measurements, these blood gas measurements show abnormalities in the partial pressures for what gases? So let's look at all of those. You tell me, do any of those look abnormal to you?
The carbon monoxide?
The carbon monoxide. The PCO is very high. Just the CO? Do the other ones look okay? The answer is just the CO, carbon monoxide alone. Let's talk about why these are normal values and why the carbon monoxide value is not for the partial pressures. So let's start with a partial pressure for nitrogen. Now, we did do a brief review of a portion of that external internal respiration lecture. And one of the slides that I wanted to go over with you before we did the section that we were focused on was a slide that showed gas exchange occurring from the atmosphere into the alveolar space, and then gas exchange occurring between the alveolar space and the pulmonary capillary blood. And we are tracking there the changes in the partial pressure, the differences, so that we could track the directionality of that individual gas movement. So here, the partial pressure for nitrogen in the arterial blood is 573 millimeters of mercury, which is normal. The atmospheric pressure is around 600 millimeters of mercury. And by the time that nitrogen gas is in the alveolar space and mixing with the air that was still in that alveolar space, that partial pressure of nitrogen drops to about 573. And so after diffusion occurs, that's what we would expect in terms of the partial pressure within the arterial blood. 573 millimeters of mercury. This would be normal. Then the partial pressure for oxygen in the arterial blood. We know that ideally, once we've had a gas exchange occur within the pulmonary capillaries, we should be at 100 millimeters of mercury. However, as soon as we leave the pulmonary capillaries, there's going to be tissues that need oxygen, and so that's going to drop slightly. Generally, the partial pressure for oxygen in the arterial blood is between 95 and 97. But we're just going to extend that and say between 95 and 100 total is what we should be seeing in the arterial blood. And that variation greatly depends on Henry's law and how much oxygen has been pushed into the plasma and dissolved in the plasma as well. If we have more oxygen dissolved in the plasma, that's going to be the oxygen that's available to tissues first. And so as we leave the lung capillaries, that might primarily be what's going to the tissues early on. Right? So there's a chance that within the arterial blood, we might get a reading of 100 millimeters of mercury, but more likely 95 to 97. Right? Partial pressure for CO2, this number is based on the same normal values we use for acid-base balance, right? When we take that arterial blood draw and we're determining the individual's partial pressure for CO2, ranges from 35 to 45 millimeters of mercury, and we're saying 40 millimeters of mercury, so both partial pressure for oxygen is normal and CO2 is normal. Now, what we didn't talk about was the normal value for partial pressure for CO, because there's not a normal value per se that we should expect for the partial pressure for carbon monoxide. In the atmosphere, there's about 0.2 parts per million is typically how it's measured, parts per million, ppm. All right, so this is in the atmosphere. And given that there's this small amount in the atmosphere, that means that there's always going to be just a small, tiny amount within the body fluids, right? So normal adult levels, just so we have something to compare it to determine how high this partial pressure for CO is for Charles. Normal would be 0.02 to 0.04 millimeters of mercury, which would reflect a very small concentration within the plasma. And this is comparatively many times higher, 0.4 millimeters of mercury. It's a much larger concentration, reflected in that partial pressure. Okay, so now that we know that carbon monoxide is the only gas here that is at abnormal levels and it's abnormally high, let's take a look at question number 2. Question number 2 states that a measurement of Charles' blood reveals that the oxygen content is low, 50% of normal. So that tells us something about one of our y-axes here, oxygen carrying capacity axis, with the oxygen content is going to be 50% of normal. And if normal is around 20.1 milliliters of oxygen percent, we're at about 10 milliliters of oxygen percent. And we can see that here right on the diagram on the next page. There's our oxygen content, and here's normal. And we're also pretty much assuming here that Charles has a normal hemoglobin concentration. He's not anemic, for example. And so under normal circumstances, he would likely have a normal oxygen carrying capacity. But given the fact that, he now has carbon monoxide interrupting the ability of hemoglobin to carry oxygen, the oxygen content He is now half what it should be because he's at 50% saturation of his hemoglobin with carbon monoxide. And if he's at 50% saturation, then that is shown here on our other y-axis. About 50%. If we're 50% saturated with CO, then we're 50% saturated with O2. So our whole curve now is much shorter than our regular oxyhemoglobin dissociation curve. Also, look at the shift that we can clearly see on this diagram compared to the normal individuals. We see the shift here to the left. And there's a few questions that we'll look at that regards that shift to the left. But right now, assuming that the oxygen content is low, 50% of normal, the hemoglobin is 50% saturated with CO and 50% saturated with oxygen, then the oxygen hemoglobin saturation curve in Charles' blood and under normal conditions shown on the next page, right? We looked at that. Carbon dioxide binding the hemoglobin is normal in both instances. That's not a problem, carrying carbon dioxide. What is the approximate percent saturation now of hemoglobin by oxygen in normal arterial blood? So we're given all this information about Charles's curve, but what we really want to answer here is what we would have for percent saturation for oxygen in normal arterial blood based on that curve. What would you say is the answer here?
97%?
You would say 97%. Why 97%, Chanel? And not say 100%?
I can't really explain, I'm sorry.
Okay, that's fine. Did anyone else choose 97%? You might have a reason why you chose that.
I did because the trace amount of CO2 and in the arterial blood will cause, will already begin to take up the oxygen when it's leaving the pulmonary capillaries.
Are you mixing two ideas there? You're saying the tissues are going to start taking up oxygen once we leave the pulmonary capillaries. Is that what you're saying?
Yeah.
Okay. All right. And that's true. That's exactly what's happening, right? And I just described that earlier when we were looking at the normal values here for oxygen. The fact that it's going to be slightly less than 100 millimeters of mercury once we leave the pulmonary capillaries, which then will give us a slightly lower percent saturation. And Nicole is also answering the same question in a different way, but it's showing us the same point here, that top curve doesn't quite reach 100 when we actually look at it, right? We don't go all the way up to 100%. We stop at about 97%. So just to note here that what you want to do is you want to look at the percent saturation at 100 millimeters of mercury or close to that if we're talking about the arterial blood. So between that 95 to 100 should represent the arterial blood. So this range here. And then we go up to our curve. And yes, if we were to draw a straight line out, we wouldn't quite reach 100. We'd be slightly lower than 100. And in terms of being slightly lower than 100, the only one that really works here would be the 97. 75 would be too low, according to this diagram. We'd be down here somewhere. So we're at about 97%. So we would say this is about the maximum we would see for saturation within the arterial blood, because as soon as the blood leaves, right, as Alexis says, leaves the pulmonary capillaries to the pulmonary veins, oxygen is being used by tissues. That then brings us to question number 3, still based on this curve here. What is the maximum amount of oxygen that can be carried in Charles' arterial blood? What is his maximum oxygen content? What would you say? Becky says 10 milliliters. Yep. 10 milliliters of oxygen per 100 milliliters of blood or percent. And we get that directly from where we max out in terms of Charles's curve here. Here's Charles's curve. Here's our maximum oxygen content, around 10. Right. Question number 4. Carbon monoxide enhances the Bohr-Haldane effect, and that's just telling us that we're going to see some sort of shifting of that curve compared to normal, either a left shift or a right shift. This means that carbon monoxide would cause a more pronounced shift of the hemoglobin oxygen saturation curve or oxyhemoglobin dissociation curve, whatever you want to call it. In what direction? Will we get a shift to the right or a shift to left with CO present? A left shift. Thank you, Nicole, which is what I showed you earlier. Here's Charles's curve. Compared to normal, it shifted out to the left. What does that mean? That means that the hemoglobin has a higher affinity for the oxygen it's already bound to. Right? It's going to take a greater partial pressure gradient at each step along the way to unload oxygen to the tissues. And so we say that hemoglobin has that higher affinity for that oxygen that it's bound. But the hemoglobin's also carrying less oxygen, has a lower oxygen carrying capacity, but a greater affinity for bound oxygen. Those are 2 ideas that I need you to remember for the final exam, right? What increases and what decreases in terms of hemoglobin's behavior. Right. Okay, so question number 5. If the partial pressure for oxygen in the body tissues is 20 millimeters of mercury, what is the best estimate of the amount of oxygen that can be released to from Charles's blood as it circulates his systemic capillaries? So we want to know how much oxygen is being released to Charles's tissues, and we're saying his body tissues have a partial pressure of 20 millimeters of mercury for oxygen, right? So what was your estimate here in terms of the amount of oxygen that could be released based on his curve? $2.5. A few saying 2.5. And Nicole, 7.5. 7.5 is important, right? But we're using it as one of our starting points here. And so what we're doing is we're saying when we leave the lung capillaries, represented here by our 100 millimeters of mercury, and we go to our tissues, well, in a normal individual that's not experiencing carbon monoxide poisoning, typically the partial pressure of their tissues for oxygen, partial pressure for oxygen of their tissues will be around 40 millimeters of mercury. That would be normal. But given the fact that Charles now has this problem where oxygen is not being released to the tissues and his tissues are becoming hypoxic, the partial pressure of the tissues is even less, at 20 millimeters of mercury. And so this represents now Charles's tissues. We're saying at the lung capillaries, the oxygen content is around 10 milliliters of oxygen %. We want to know what the oxygen content will be of that blood once we get to the tissues here that have a partial pressure of 20. Right? And then we take the difference to determine how much oxygen then was released to the tissues by looking at how much oxygen still remains within the arterial blood. So we go up to the curve, and then we go out to that axis here from this point. And I believe Nicole gave me that value. We're around 7.5, right? How do we estimate that? Well, it's a little bit of guesswork here. If you look at some of these other numbers, right? In terms of the estimate that we would make, none of them would really match that point. So 7.5 is the best estimate based on the final potential multiple choice answers. If we started with 10 milliliters of oxygen per percent, and now we're at 7.5 within the blood, once we've reached the tissues and we've had oxygen be released, we know the difference then between 10 and 7.5 gives us the quantity of oxygen released to the tissues. 10 minus 7.5 gives us this 2.5 milliliters of oxygen. In Charles's blood, the partial pressure of CO in the blood is far lower than the partial pressure of O2. Right? We already looked at the partial pressures for both of these. Let's make a note of what they were. Partial pressure for CO for Charles's blood was 0.4 millimeters of mercury, while for PO2, I believe it was 95 millimeters of mercury. So that partial pressure for CO much, much lower, fraction of what it is for oxygen. And yet we see the percentage saturation of hemoglobin by oxygen and CO is 50-50, half and half, right? This result indicates that the affinity of hemoglobin for CO is approximately how many times greater compared to O2. Now in the lecture itself, there is a number given in terms of the magnitude of affinity that hemoglobin has for CO over O2. And it doesn't quite match the numbers that are shown here, but we can estimate what that would be by comparing these partial pressures, right? And that's what we would do. If you were using the value that was given in the lecture itself, right, it would be closest to what value here?
238.
238, right? And Becky says over here that you're dividing your partial pressure for oxygen by the partial pressure for CO, right? We want the ratio between them so that we can determine the difference. So in the lecture, I believe we talked about the fact that O2 compared to CO was this ratio here. For every one CO molecule, right, we have attempting to bind to a hemoglobin binding site, we have 210 oxygen molecules. And there is a 50-50 chance that either that one CO or that one of those 210 oxygen molecules will bind to that site. That's how much the affinity for hemoglobin compares to oxygen. It's much, much higher. So we would do the same setup here, but as Becky says, we can use the partial pressures because they indicate something according to Henry's law about the concentrations of these gases. So now we just set up that comparison here, oxygen at 95, CO at 0.4. And then we simplify this ratio, right, to show that we get 200, I believe when you actually divide it, 237.5 to 1. Round that up, 238, right? So the affinity of hemoglobin for carbon monoxide is 238 times greater than the affinity to oxygen. So once again, that's oxygen to CO. And we can set up the same scenario here. We can say, well, this would be like one carbon monoxide attempting to bind at a site while there's 238 oxygen molecules attempting to bind to that same site. And it's a 50-50 chance that that one CO will bind or one of those 238 oxygen molecules. Right. Next question. Would you expect Charles disorder to be accompanied by chemoreceptor-mediated hyperventilation? Oof. Let's break this down a little bit. Hyperventilation means they would be doing what in terms of changing their breathing?
Increasing their breathing rate.
Increased breathing rate. Anything to the tidal volume?
Increasing tidal volume as well.
Awesome. Increased tidal volume, right? So both of those would increase. In perhaps an attempt to get more oxygen in, more CO2 out, what have you. And in terms of this change occurring, right, we know the chemoreceptors, and this is in the review that I did with Monday, Wednesday people, the chemoreceptors are primary and secondary chemoreceptors are sensing the partial pressures for oxygen. That's the function of the secondary chemoreceptors. They're found on the aortic arch, carotid arteries, and the primary chemoreceptors found in the medulla oblongata. Those are sensing hydrogen ion concentrations indirectly via the partial pressure of CO2. And that's all that these chemoreceptors can do, is they can detect partial pressure of oxygen, partial pressure of CO2, or hydrogen ion concentration, right? Those are the functions. And in response, the medulla oblongata can utilize that information to say partial pressure of oxygen is much too low. If it's below 60 millimeters of mercury, right, that's when we generally see this hyperventilation begin. The medulla oblongata respiratory center then triggering that increased breathing rate and depth of breathing. And then for the hydrogen ion concentration detected by levels of CO2, the greater the partial pressure of CO2, the more likely we're going to see that hyperventilation occur. And that's, keep in mind, the primary signal that causes changes in ventilation is the partial pressure of CO2. Partial pressure of oxygen, that's secondary to that. Partial pressure of CO2, when that's above our 35 to 45 millimeters mercury range, that's when we would expect then to see the medulla oblongata respiratory center begin the process of triggering that change in ventilation, increased breathing rate in tidal volume, right? So in the case of Charles having carbon monoxide poisoning here, would you expect him to be hyperventilating? Do you remember anything in the intro there in terms of his condition where it said he had dyspnea, shortness of breath, or that he was experiencing hyperventilation? Any type of change in breathing pattern? Alexa says, is it going to be no? And the answer is, yeah, it's going to be no, right? He was breathing normally, couldn't see very well, and then he felt lightheaded and he passed out, right? Didn't say anything about him changing his breathing pattern. Becky says, no, this is because the partial pressure of oxygen is normal, right? And that's definitely the case here. Partial pressure for oxygen falls within normal range. We wouldn't see our secondary chemoreceptors triggered in this case. We're at 95 millimeters mercury. We're not at 60 or below. Same would be true if one of the options here was no, since the partial pressure of CO2 in his blood is normal. That would be the more accurate signal that would in this case lead to potentially hyperventilation, as if that partial pressure of CO2 was higher than normal. But we don't have a problem with the levels of oxygen or CO2 dissolved in the plasma, right? This is a problem with hemoglobin being able to carry oxygen. And so the chemoreceptors are not responsible for detecting how much oxygen is being carried by hemoglobin. So the correct answer, yes, here is D. Next up, our last page here. Question number 8, fundamentally, Charles' condition is a problem of what? How would you describe his condition? A, B, C, D, or E? Alexis says C. Anyone want to disagree here? Jessica says he can't transport the oxygen. That's completely correct, right? It's not a problem with pulmonary ventilation. His ventilation's working fine. Actually, he's breathing normally, right? He's not hypoventilating. And we know that he's breathing fine because his partial pressure for CO2 is normal. Not getting rid of too much CO2 with hyperventilation, not trapping CO2, right? So that's an indicator that his rate and depth of ventilation is normal. B, diffusion across the respiratory membrane between that alveolar space and the alveolar capillaries, the pulmonary capillaries. The gases themselves can move across that epithelial tissue. It's not a gas exchange problem here. Not like we see with some respiratory disorders, where we actually have problems moving those gases at a normal rate. Something we might see, for instance, with our obstructive and our restrictive disorders. Then D would not be an option because it's saying exchange of dissolved gases between the blood and the interstitial fluid to the tissues in the body. The key here as to why this is incorrect is there's no problem with the dissolved gases. Those are at normal levels within the plasma. And that's actually the only oxygen really that the tissues have access to, is that's dissolved in the plasma due to this carbon monoxide poisoning. Then E, absorption of oxygen and release of carbon dioxide by cells in the peripheral tissues, right? The cells themselves are diffusing oxygen and CO2 at normal levels. They're just not getting enough oxygen, because as you all said, the problem here is that the hemoglobin that is responsible for the bulk of oxygen transport within the blood is not transporting the oxygen properly, not carrying enough, and it's not releasing enough to the tissues due to its increased affinity for that oxygen that it's bound to. So yes, this is a transport problem. The oxygen unloading is reduced, the oxygen carrying capacity is reduced. Now, number 9 is a weird question, but hopefully when we break it down, it will make a little more sense here. If we had to make an analogy between this carbon monoxide poisoning that Charles has and one of these other disorders, which would be the best match here? What would you say, A, B, C, or D? Jessica says anemia, right? And you might overlook this one because you might say, oh, he's not bleeding profusely, so it can't be analogous to that. But if we remind ourselves what the basic definition of anemia is, it's a reduced oxygen carrying capacity, which is definitely what Charles has in this case. It doesn't matter that he's not bleeding profusely. He has anemia at this point, acute anemia, because of the carbon monoxide poisoning. Right? Why would the other ones not work? Well, A, barbiturate-induced hypoventilation. Keep in mind that this isn't a problem with ventilation. He has normal partial pressure of CO2. So we know that his tidal volume, his breathing rate is normal, right? He's not hypoventilating. B would not work here because altitude sickness would suggest that there is a lower partial pressure, atmospheric partial pressure. PATM would be lower with the problem with altitude sickness, which would be why the CO2 is being lost at a greater rate, potentially producing a respiratory alkalosis for the individual. And the oxygen has problems diffusing in due to that change in PATM, atmospheric pressure. So given that there's no indication that that there's a change in the atmospheric pressure, we don't see here a problem with gas exchange once again. And then emphysema is a gas exchange issue. We don't have a change in the diffusion rate. As we said earlier, we have normal diffusion across the respiratory membrane from the alveolar space into the capillary blood. That's not a problem, right? The problem comes with trying to then load the oxygen onto the hemoglobin and then release that oxygen once it is bound. Question number 10. Which of the following treatments here is not an appropriate component of what would be an aggressive treatment plan for Charles's disorder? What would you not want to do for him here? It would be a bad idea. And by bad idea, I mean it would only make his condition worse.
B, alkalization of the blood, so increasing the pH. That's not an appropriate amount.
Okay, all right. So Chanel says B, and Kenny also said increased pH. Why would it be a bad idea to increase the pH of his blood? Kenny said more left shift. Exactly. If we think of the variables that that we talked about in that last lecture together, when we were looking at the left shift and the right shift, we had temperature, we had partial pressure of CO2, we had that 2,3 DPG, and then we had pH, which is based on the hydrogen ion concentration. And compared to normal, when hydrogen ion concentration is greater, right, we get a right shift. And when hydrogen ion concentration is lower, which represents alkalization of the blood, right, then we get a left shift. And Charles already has a left shift. So we don't want to shift that curve anymore, because that means that the hemoglobin will hold on to the oxygen that it's already carrying even tighter. We don't want that to happen. If anything, we want to do the reverse. We want to cause a right shift to help push that oxygen off, which is something that we can do here. For instance, D might not seem like a good idea when you think about it. Well, why would you want to give him elevated levels of carbon dioxide if he's having a problem with getting oxygen to his tissues? Well, adding more carbon dioxide into the blood means that we have the ability to shift that curve towards the right, increasing PCO2. So curve is left shifted. Let's try to shift it back to the right. Let's try to unload some of that oxygen to the tissues. Why is that possible? Well, that CO that we're adding can physically attach to the globulin chains, the alpha and the beta, and help cause that shape change that allows that the iron ion to release the oxygen. That will more readily occur if we load up the blood with more CO2. How about A here? Why would that actually be an appropriate treatment? Well, with a breathing gas mixture that has a high percentage of oxygen, that means we're going to have a higher partial pressure of oxygen that the individual is now taking into the alveolar space. And according to Henry's law, we're going to have a higher concentration of oxygen dissolved in the plasma. And that oxygen is readily available to the tissue. So at least they're getting some oxygen. It's not a significantly higher amount, but it's part of an important course of treatment here to try to get more oxygen to the tissues. So higher PO2 means that, according to Henry's law, we're not changing the solubility of oxygen, but we are changing the pushing pressure from above within the alveolar space. This increases, and so the concentration dissolved in the plasma would increase. And then C, partial blood replacement with normal compatible whole blood. You can see why that would be helpful here. Remove the affected red blood cells, the red blood cells that have the CO bound, and also holding the oxygen hostage, and replace those red blood cells with new red blood cells. So that would be useful as a course of treatment. So everything here can be used except for B to treat Charles. So expect 2 or 3 of these questions, either questions directly from this case study, or very similar to these questions here in the case study on the respiratory portion of this final exam. So make sure that you do go back and you review this material, right?